duplicate token, and impersonate logged on user. This is an interesting little sequence, and when we looked up this little sequence of stuff, we found some code on Google Code. This is code used to bypass the device driver signing on Windows. And if we take those two pieces of code and we overlay them, we see they line up very nicely, and that hints at a process. It hints at going back, taking this, turning it into a general pattern. So replacing some of the specific stuff in there with no cares or with the pieces that link it together. So you see the H token in green has to be the same H token, has to duplicate. You see that in the next one, the HB token has to be the same HB token has to launch up to impersonate logged on user. So we replace those with variables so they line up, and we can identify that pattern wherever it occurs. And in fact, that's what we do. We call those behavior specification units. There's a high-level language that makes them very easy to write. If you can write programs for Windows, you can very easily write these. If you're not quite up to writing programs for Windows, you can probably still write these because it's a very simple language geared toward writing these patterns. What happens, of course, is these patterns get compiled into a nasty mass that you never want to see, and that's okay. That happens behind the scenes. So here's a snippet of one of our BSUs. This is one we use to recognize anti-sandboxing techniques. So if you match this, you're probably malware. We took a lot of these from Paranoid Fish, which is found at the bottom there. Paranoid Fish is an example of various anti-sandboxing, anti-debugging techniques. And you can see we represent a DSU. So there's a DSU somewhere called check for small disk size, there's one called check for mouse movement, etc. And it's in the rules at the bottom tells if you match any of those, under any conditions, we want to apply this anti-sandbox tag to that piece of code. So we can look for any of this stuff. If Hyperion finds any of this in the call traces, it labels it as anti-sandboxing, and then you can go and look and see what's actually taking place there. And it's easily expanded as we write. In fact, this is a snippet of the larger one. As we discover new kinds of anti-sandboxing, we just add another DSU and a rule to it and easily expand it. Here's our keylogger detector. In full. So somewhere there's a DSU called get key press. It's what you might imagine. It's all different ways on Windows that you might select key press. All by file write complete, and that's all different ways in which you would write to a file. We have a couple of things going on here. One is key press has to be the same in both. So we know that the key press that was read is the one that's originally written. File is part of the file write complete BSU, but we don't care about it here, so we just say we don't care. And the rule says that I have to have V1 followed at some point by V2. Things can happen between the two. Things can happen, and any DSU that matches either one of those is fine. And things can in fact happen in different functions in different parts of the code. The point being, if I find a new way to read a key press on Windows, I just add that to the get key press DSU, and nothing else has to change. If I find a new way to write it, I add that to the file write, nothing else has to change. If I get interested in people writing key presses to the network, well then I add a new line that says network write complete, and be sure that the key press is the reference there, and I can add a second rule, which then says V1 followed by presumably V3, and either one of those would catch this. But the point is, DSUs are very simple. They're just simple, they're easy to write. They're pretty easy to read. They have a few special symbols in it, but not that much. The dollar signs, the variables, underscores, don't care. You can learn that very easily. They're very extended and they're very robust. So here's a slide example of it. Here's some bytes from an actual piece of malware. This was the malware that was used to attack Oak Ridge National Laboratory back in 2011. That we captured. We can disassemble it. That is part of disassembly. And for those of you who love reading disassembly, this is great. You can structure it. So you turn this into what you do call recognition. That means structuring. And so we see if and else is popping up. We would see while loops, etc. And that could be helpful. But let's turn it into a call sequence, because that will surely clear it all up once we see the call chain. So there it is, and I'm sure that clears it all up. You can see what's going on: open process, virtual allocation, write process, etc. A lot of stuff in here. But the Hyperion system does the bookkeeping, boils all this down to the one thing you really care about, which is that that piece of code is doing process injection. So we get a BSU match, it matches across all the bytes, and it says, this piece of code is doing process injection. The first argument, I believe, specifies the process into which you're going to inject. The second one specifies the code you're going to inject. And the third is a delay, so that you can hopefully avoid detection. And we get that without actually executing any of it. We match it, we can see which parts of it match that and what's going on. So, again, this is the summary of where we are. PLL 8, we've delivered this to organizations. It seems to be working well. We're collaborating with folks at the Applied Physics Lab, at Lawrence Livermore, at Pacific Northwest National Laboratory, and at Sandia National Laboratory. The term rewriter that is used in the system is open source, so if you go to GitHub, you can go and grab that. We have about 237 behavior specification units, which allow us to match a very large corpus of malware. We have our own malware corpus here. We work with external organizations that have their own, and so we're routinely looking at our coverage of this. We've got right now 237 BSUs, and we're doing really good matching, and that is about 3,500 lines of BSU, non-comment statements. So you can see doesn't take a whole lot of writing to get a BSU that's going to be very robust and match a lot of bad behavior. Presently, our top-level malicious BSU finds a whole bunch of good stuff. It finds process injection, service enumeration, key logging, anti-VM, anti-debugging, uploading and downloading behavior, and a whole raft of others that we've introduced to catch all the malware. So that's the status of the system, and I'd be happy to answer any questions you have about it.
This is Dan Trellis at Rapid Scan Labs. I had a question about, maybe you could go a little more detail into the type of testing that was done in the national labs.
So the Hyperion system was selected by the Department of Homeland Security for its Transition to Practice program. And as part of that, we delivered the source code, the documentation, etc. to Sandia National Lab. And they did a pretty thorough red teaming of it. They red teamed all the technologies that were selected for this program. and created a comprehensive report of it. And I believe that report is available. So, David is nodding his head at me, so that report's available if you'd like to see that. They deployed Hyperion on their farm malware repository, and to the best of my knowledge, I talked to Steve Hurd, they were still using it there. So it's been vetted by them. It's been put through its paces at 2 other organizations as well. Who both done that. I don't think those reports are publicly available. And David shaking his head at me, which means no. But it's been through some pretty significant testing. Like I said, we have our own malware catalog here that we routinely run it over, and at least one of our other partners has a pretty comprehensive malware repo, and they would pretty routinely run it over that and to see what they can catch it and discover.
All right, thanks.
Sure. What else can I tell you?
No, nothing else. Thank you. That was good.
So there's one question that came up. Can you describe where this may be in use without going into details of who is actually using it? So I guess I can mention that there's a commercial company, R&K Cyber Solutions, that has licensed this for commercial use, and they are, and I think they're repackaging it to have nice reviews, etc. But we didn't tell that much about here. It's been used by a number of other government entities have requested it from us under the government use rights, and we delivered it to them. And a couple of them are still in pretty close contact with us. We know that they're using it. I can tell you that they're using it to screen the software, and in one case they're using it for its original purpose, which is to analyze malware. So they're using it pretty heavily. I don't think I can name any of them, unfortunately, but it's in use. I'd say there are 6, maybe 7 organizations where this has been delivered and is in use. And as far as licensing goes, we have licensed it to one company, but we're licensing it on a non-exclusive basis, so we intend to license many more copies of this. I think we'll be the first second company that I think I'll put it to you. So one thing I didn't do today was show you a live demo of the system. I'd be happy to do that. It's very text-oriented, because it's intended to be run sort of behind the scenes to scan software. There is an interactive version of Hyperion called the eViewer, and if you'd like to see it, we can arrange a time to actually do a live demo of the system for you, but that's not within the scope of the time I had available today. Okay, I don't believe there's any other questions, so thank you, Stacey, for giving your time on this and going over this. Dan, do you have any other questions?
No, I don't. Thank you.
Okay, thank you. Hello, and welcome to Oak Ridge National Lab's Invention to Innovation webinar series. Today's presentation is on Hyperion cybersecurity technology that will be presented by Dr. Stacey Crowell. My name is David Sims, and I'm Commercialization Manager here at the lab. If you have any interest in licensing this or other technologies from the lab, please feel free to call me at 865-241-3808, or you can find my full contact information on the web at ornl.gov and follow the Our People link near the top of the webpage. Before getting into Stacey's presentation, I'm going to take a couple of minutes to give you an overview of cybersecurity technologies and capabilities here at the lab. We have over 30 researchers in the Cyberspace Sciences and Information Intelligence Research Group who conduct research in cyber warfare, situational understanding, visual analytics, and information dominance. This research is done in order to defend the nation's critical infrastructures against cyber attacks, to understand threats, in order to provide real-time, actionable intelligence, to secure supply chains and continue operational capabilities, and to defeat both known and future adversaries. The group is divided into 2 research teams, the Cyber Warfare Research Team and the Situation Awareness and Visual Analytics Team. Our guest presenter today is the leader of the Cyber Warfare Research Team, which currently consists of 13 people, 6 of whom hold doctorate degrees. The team studies methods of both attack and defense in cyberspace, and also manages the lab's Center for Trustworthy Embedded Systems, which operates a cutting-edge laboratory conducting research on the security of vehicles, medical devices, as well as the rest of the Internet of Things. To support this research, the team also operates and maintains its own private test networks, computational clusters, and storage units. The current research efforts include learning-enhanced moving target defense, physics-based intrusion detection systems, improvements in Internet routing for enhanced resilience, and static analysis of compiled software, an example of which will be presented in today's webinar. Dr. Crowell is the Chief Cyber Research Scientist here at Oak Ridge National Lab, and his work focuses on applying high-performance computing and computationally intensive methods to understand automated reverse engineering, semantic analysis, system composition, and software forensics. In addition to being leader of the Cyber Warfare Research Team, Stacey also serves as the program manager for the lab's cybersecurity for energy delivery programs and holds a joint appointment in the Electrical Engineering and Computer Science Department at the University of Tennessee. Stacey has managed commercial software development projects and has consulted on the design, development, and testing of a wide range of applications. He also holds a PhD in computer science from the University of Tennessee. More information about our technologies available for licensing can be found on the web at ornl.gov by following the partnerships link, which is about midway down the webpage. And in the next day or so, we'll have this webinar posted on YouTube, as well as a link to it posted on our partnerships website. So now I'm going to turn the microphone over to Stacey, who will provide a 15 to 20 minute overview of Hyperion, and afterwards he'll be available for questions. If you want to ask questions, remember to unmute your microphone, or you can email me questions at simsdl@ornl.gov. That's simsdl@ornl.gov. Okay, Stacey. Great, thank you, David. And do feel free to interrupt me as I'm going through this and ask questions if you'd like. So I'm going to tell you a little bit about Hyperion, and I'll try to get my 2-hour presentation down to, what did you say, David? He said, what, 1 hour? 15. Okay, well, maybe. let's see, this will work. Let me see if I can change slides with it. And it looks like I can't. Can you let me do the next slide, please? Perhaps slide changing is a technology we need to work on. All right, great. We conquered the slide advance. That's a wonderful thing to good technology to have on our phone. So really, hikari is trying to get at this problem that software tends to be delivered to you as a black box. It comes to you in this nice compiled form, ready to execute, and that's all well and good, but it contains programmed but unknown behavior. It may contain some ill-conceived behavior, poorly implemented protocols, weakly implemented crypto, weak random number generators, things like that. And it may contain correct behavior that is correct to specification, but still insecure. And we need a way to discover all of this before adversaries do. We do have someone who will find all this for you, but your adversary. But we would like to know about it preferably before they do, because then we can take steps to deal with it. Wow. There we go. What we need is rigorous assessment of the true functionality of programs. We need to be able to take a piece of compiled software and see what it does. It's a hard problem, but it's made harder by a number of factors. One of them is compilers. Compilers will come along and add value. They will they can strip out secure behavior, pretty well documented, and they can introduce compiler bugs. They add their own little features to it. So you have to work with compiled software in order to get things done. And you have to consider all the behavior. One of the things that will lead folks astray is the use of heuristics early on. It seems reasonable to conclude that incrementing a register is the same as adding one to it, but on Opinion they're not quite the same. So that little highlighted line there shows you that one will modify a flag called the K flag, the other will not. And you think that's not a big deal. That is, in fact, something that you see in malware. People can take advantage of this to determine whether or not they are being sandboxed or they're being emulated to debug, because emulators will tend to get this wrong. The intuition of people reading the code, they'll tend to get this wrong as well.